Hi, my name is Amit and I'm really excited to present to you this work for this year's MICCAI entitled Do We Really Need That Skip Connection? Understanding its interplay with task complexity. I work at the Medical Image Analysis Lab here at the University of Bern in the RTOG Center for Biomedical Engineering Research, and our collaborators also represent the University Hospital Zurich and PSI. In the next roughly 5 minutes or so, with our friends from South Park, we will try to get an overview of this work. Note the QR code on the top right of the slide. This points to our GitHub and will contain more details and links for further reading. Let's get started.
Yet another unit paper, eh?
Yes, indeed. UNets are ubiquitous in medical image segmentation and more. However, there's not much understood about its defining feature, which is the skip connection. Prior work mentions that it helps with gradient flow for more reliable training and passing high-frequency content directly into the decoder. The question, however, we ask is, how does the texture content in the foreground and background of the image impact architecture choices we make, particularly with respect to the skip connections? To investigate this, we choose 3 categories of architectures: no skip, where the skip connections have been severed, standard or vanilla, and enhanced, like the attention-gated unit, where there are more or enhanced skip connections. Beyond MICCAI, we extend this to 2 flavors of architectures in each category with the VNet and UNet++ as well. We test first with synthetic data with different blends of foreground and background textures, the difference in which is measured using a novel metric called texture similarity. Then we test further with medical images as well.
Synthetic textures in medical images? What?
Okay, let's delve into this further. The 2 plots on the top are read as follows. The horizontal axis is texture similarity, going from more similar in the left to less similar on the right. The vertical axis is the distribution or frequency of images. Intuitively, more similar foreground and background will mean that the segmentation task is more complex for humans as well as for deep networks. Now, each curve is a level of foreground or background blending, with red to yellow being harder and green being easier. This can be done by either blending the background into the foreground, which is on the left, or foreground into the background, which is on the right. Results from this extended work is still under review. Below, you see the same texture similarity variations for 4 medical image datasets in the public domain: breast ultrasound, colon histology, heart MRI, and spleen CT. We vary the texture similarity by adding speckle noise to the entire image or by selectively blurring the background only. These form our test cases when the model is trained on texture unperturbed data.
Okay, so what do you want me to learn from this?
Yes, Dan, we're getting there. Here are some quantitative results using the dice similarity coefficient as a metric. There's more on the GitHub link above, so check it out. Let's take the example of breast ultrasound and look at 3 levels of texture perturbations: harder with speckle noise, in domain, which is the same as the training textures, and easier, where the background is selectively Gaussian blurred. Note that in the harder case, the no skip UNet performs better than both the skip connected versions. For the in domain and easier cases, the attention gated UNet is the winner. The same observation is made for the spleen CT and heart MR cases, showing that severing skip connections can lead to a more robust performance in case of texture variations in the test set. Isn't this really interesting? I hope this convinces you that not all skip connections could be good.
Numbers, show me some real images.
Okay. When Kyle asks for images, we present them. Let's look at the spleen CT results, for example. The middle row is unperturbed texturally. The second column is the ground truth segmentation, and the 3rd to 5th columns indicate attention-gated UNet, the vanilla UNet, and no skip UNet results, respectively. Note how varied they are. We train with the same seed, same initialization, to the same number of epochs, with the only difference being the architecture. The harder case is where it's most interesting. We see similar and interesting results for the other medical image datasets as well. More details about this in our paper. To learn more about this, please visit our poster at MICCAI or scan the QR code on the right top corner. Thanks are due to my co-authors Jonas, Nikolaus, and Mauricio, seen here to my right, and the Swiss Cancer League for funding our work. We look forward to discussing this with you in more detail. See you soon.